All right, so to catch up, for those of you that are just getting this video going, sorry. We're comparing dependent populations, and the types of dependent populations we're working at are ones where there's a before and after case. All right, so we've set up a problem here where we have some students who are taking an ACT class to improve their ACT scores, and here are the before and after data. And the key to this, folks, is that you don't have to look at the hard data. All you have to do is look at the difference of the data. So what's 25 minus 20? 5. 24 minus 18? 6. 2. 1. 6. 5. Negative 1. Be careful that you subtract correctly. Don't say that this number is positive 1, right? If you're subtracting in a specific direction, always be consistent, all right? And so if a number winds up being negative, let it be negative. It's okay. 10, 3, 2, 2, 3. And the key to solving these problems, or coming up with a confidence interval for showing the true difference, is that we are going to work off of this difference data instead of the actual hardcore data. All right? Use the newly created difference to compute a confidence interval. All right, did I tell you what percentage I wanted?
Nope.
Okay, let's suppose I wanted a 95% confidence interval. Just so that we have something to work with. So when you work with this data, folks, the cool part about it is that, again, like I said, you basically just work with the difference values, all right? The confidence interval is going to be D bar. Guess what D bar is?
Difference.
The average of the difference, right? Okay? So D bar is the mean of the difference. So that's going to be the center of your confidence interval. And your E, you're just going to calculate almost exactly the same way we did back in chapter 8. All right? For the whole thing.
Okay.
It's T crit times the standard deviation of our D's divided by the square root of n. And this should look like a very familiar formula. It's exactly the way chapter 8 looked for a small sample size confidence interval calculation. All right? So basically we've taken this two populations and broken it down into essentially one population that represents the difference between the two populations that we are working with. So, how do we calculate D bar, folks? Yeah, it's an average, right? It's a mean. So add up the D's and divide by the number of D's, all right?
3.9 change.
All right, so what I'm going to do is actually put them into my statistical calculator, because I also need to calculate S sub D. Guess what S sub D represents? This is the sample standard deviation of the differences. So you basically have to calculate what the standard deviation of those numbers is, okay? So this is our old chapter 3 stuff, where it's the sum of x minus x bar squared, all divided by n minus 1.
Let's see. How many twos were up there? 3. How many ones were up there? Just 1. We did 6s to 5s. There's 1 negative 1. 4. How many 4s were there? 1. 10s. How many 10s were there? Yeah. Alright.
So you got 3.9333333 for the mean. Alright. So let's just round to the tenths for D bar. D bar for our data is 3.9. Now, technically, how would you guys calculate the standard deviation? Technically, the way you would do this is you do the sum of D minus D bar squared all over n minus 1, and then you would take the square root of it, right? The old chapter 3 technique for calculating standard deviation, okay? I would suspect that at this stage, you guys would probably go to a software package, plug the numbers in and say, calculate the standard deviation, or use a calculator to do it. A lot of calculators have the ability to enter in the data. And what I got calculated for the standard deviation is 2.66. And assume that I did it correctly. Again, technically you guys were doing this, and you went through the whole rigmarole and got that. I'm not going to force you to go through it again, even though you will on the homework at least at some point in time, because you're going to get asked to calculate some standard deviation. And whatever technique you use is fine, folks. I mean, if you go old school and do the whole long, drawn-out stuff, that's fine. If you use a software package to do it, you just read off the number at the end and use it, that's fine too. I am happy either way, okay? As long as you show me that, you did something to figure this out and weren't just pulling it out of nowhere, I'm okay, all right? All right, so I've got now my D bar, my S sub D. Now all you have to do is tell me what T sub C is and what N is. First off, what are going to be my degrees of freedom? Guess what they're going to be? You always do n minus 1 for degrees of freedom, okay? So it's not 15, but actually 14, okay? So when you look up T critical value, look it up for 14. And again, please use table C as in cat. So, and I said 95%, right? Uh-huh. And again, use the 0.05 area in two tails table. 2.145. Did everybody see where I got the 2.145 for my T critical value? Yep. You got your wheel? All right. Jason, Haley, you good?
What was our percentage?
95%. Alright? So my E, 2.145 times my standard deviation, 2.66, over square root of 15.
Square root of 15.
1.473. Technically, our D bar went to 3.9, our standard deviation went to 2.66. We're probably good going to 2 decimal places. E is 1.47. So what is our 95% confidence interval?
So do minus the 3.
Nope. We'll do the -3 in the next chapter. I was getting ahead of myself. 3.9 plus or minus 1.57.
4.7.
1.47?
He said that. He said
You said 1.57 and you wrote 1.47, so I was
Okay.
looking down, I didn't see what you wrote.
Okay. Do what I write, not what I say, apparently. So what is 3.9 minus 1.47?
2.43.
And what is 3.9 plus 1.47? And so again, we are basically 95% confident that the true increase is somewhere between 2.5 and 5.37. So does it make sense for them to say that 3 is a reasonable number? Yeah, and not only is it a reasonable number, but it's actually on the lower end, right? They probably could have said 4, or if they really wanted to, they could say, hey, we're 95% confident that might even be 5, right? Because that's all of those numbers are within your 95% confidence interval. And that's the sort of stuff that statistics allows companies to truthfully say about their product, right? In theory, if they were doing proper statistics and you trusted them that they were doing it, this is how they should be doing it, all right?
So hypothetically, you could make it 99% confident interval, and then it could be even wider,
Yes.
and you can pick a number on the top end.
That's absolutely right, and there are definitely businesses that would go that route, more than likely. Again, and this is why you should ask, right? Where did the data come from? How did you get that number 3? And if they show you this, and they say we use 3 because it's the safest number that fits in our 95% confidence interval, you may even think that that company is being more honest than not, and you'd say, hey, I am willing to use you, et cetera, et cetera, et cetera. Whereas if someone said, here's my 99% confidence interval, and that goes from like 1.2 up to 7.3, and they said, well, we used 7 because it was still within a 99% confidence interval, right? Again, then at least you have all of the real information that you can base your judgment on. You very rarely get that, though, right? But this is the sort of thing that you guys should do. If you're going to look for this sort of stuff, if you say, if they're advertising this, you should ask how, why, show me the data, all right? And even if they made the data up, at least if they can show it to you, it means that they know how to do it. That would be at least nice, right? I mean,
So why would they choose, like, why would they not try and use a higher percentage of 98 or something like that to get a better idea? Wouldn't it be closer to that 3 though?
oh no, the higher this percentage goes, the wider the range
A
becomes.
little wider?
Yeah, because they're trying to guarantee that the real value is inside of here. So if you want to be more sure that the real value is in here, it will actually have to be bigger. Basically what happens is that at 99%, our t-value will go up to like 3.2. And so these numbers will spread out even more. So,
Honestly, I think, I don't know, I feel like that makes no sense why. Because I feel like if you're gonna be that much more sure, you should have a smaller number.
you're not trying to say what the number is. You're trying to say that the number was within a range. Because we don't know what the real number is. I mean, the real number could be anywhere, I mean, again, it could be like -7 for all that we know, right? But we're just saying that we're pretty sure that we're 95% sure that what the increase is somewhere between these two numbers. Is it really 3? I don't know. Maybe it's 5, maybe it's 8, and it's in the 5% range. We don't know. It's
But
just,
that's what we're trying to prove.
yeah, we haven't gotten there. That's chapter 10 and 11, is to say, can we say that it's more than 3, right? So technically, if this company was claiming that they're 95% sure that it's more than 3, they're lying, right? Because under a 95% confidence interval, it could be somewhere between 2.53 and 3, which is obviously less than 3, and therefore they'd be lying. if they had said more than 2, if they're 95% sure that it's more than 2, this actually validates it, right? Because they're 95% sure that the number of increase is somewhere between 2.5 and 5.5, and those numbers are more than 2. That would actually be a truly legitimate statistical claim. Again, that's more for chapter 10, but I'm prefacing it because that's kind of why we're doing these sorts of things, is to be able to say those sorts of statements, right? So if you guys, if you guys come up later on in your careers and you become statistical analysts, or maybe you become financial analysts, or you become, trainers, and you want to prove that you are going to increase muscle mass by more than 10%.
I'll accept that answer.
Exactly. So you would say, here are my 8, current people that are using me, and here's what their their muscle mass was before me, here's their muscle mass after me. If the value of your 95% confidence interval is like somewhere between 12 and 17, you can say yes. I'm pretty sure that it's more than 10, because 12 to 17 is more than 10. And that's a legitimate statistical claim. And that's what you guys want to be able to do, right? I mean, at least that's what advertising agencies want to be able to say. And if they can actually say it truthfully, it's like, wow, even a double bonus, right? Just not often that you really actually believe the statistics that any company generates, right? But if they can show it to you and actually walk through the steps and say, here's how we did it, you'd be like, no, hey, I've actually even seen that. All right, so let's try one from the book now and see what it says, or see the kind of examples it has in there. So let's see, what did I assign in 9.3?
A bunch of even numbers.
You're kidding.
Only a little.
4, 8, 12, 16, 20.
4, 8, 12, so all of them,
Really like those exact numbers.
they're multiples of 4. What? Those are great numbers.
Well, I'm just saying, like, every chapter has probably the same amount for the same unit.
Yeah, because they put in about the same number of questions for every one, too, so it fits, right? All right, so, how about we do question number 18? Talks about a teacher who gets ill and has a new teacher sub in for him, and they're trying to determine, was the first teacher better than the new teacher, right? So let's see how it works, right? So here are the grades, right? So how many were there? 12? 12? That looks like 12, right? So here are their before and after scores, right? For instructor A and instructor B, right? 58, 52, 82, 60, 78, 83, 91, 90, 83, 87, 77, 70, 45, 48, 87, 81, 94, 90, 92, 90, 68, 71, 77, 70 for the 12 students in his class. Some upper level biology class, supposedly. All right, so we want to create a 90% CI for the difference between instructors. The difference between A and B. All right, so what are we going to do? Compute the difference, right? So what are the differences of all of our data? And And again, just be consistent when subtracting, okay? If you go with negative numbers on the first one, just make sure that you're subtracting that way and be consistent, right? So I'm just gonna subtract top to bottom because that's the way I wrote it, right? So, true, again, you can just redefine it if you wish, right? 82 minus 60, 22. Note, 78 minus 83, since I'm going top minus bottom, that's negative 1, negative 4, 7, negative 3, 6, 4, 2, negative 3, 7. Alright. 2 sixes, 122, -5, -1 and 1, -4, 2 sevens, right? 2 -3s, 1 6, 4, 1 2. Oh, I have been 13. Crap. I screwed up. Dang it.
Just add it and divide by 12.
I have to get the standard deviation too.
That's our friend.
Alright, so there were 2 sixes, right? There's 122, there's 1 negative 5, there's 1 1, there's 1 negative 4, there were 2 sevens. Oh, there's only 1 negative 3. There we go.
There's 2 negative 3s.
Oh, there are? Dang it. There's 1 6,
Why don't you start at the top and go down?
there's 1 4, there's 1 2. She looks like I have it, right? So this. Yeah, I'm getting 3.5 at the moment.
Wait, for what?
For the mean, I was getting 3.5. That can't be right, right?
I was getting
It's not.
3.33.
Say how you. Duh.
I'm not small, I am.
1 and 1. Negative 4. 2 sevens. Alright. First number is 6. Second number is 22. Third number is negative 5. Fourth number is 1. Fifth number is negative 4. Sixth number is 7.
2 negative 3s.
Seventh number is negative 3.
6 more.
Oh, I have 6 in there twice. That explains it. And I have 1 4, right? I have 1 2, right? Alright, let's see if that worked out.
Oh, mine says-
Okay.
Delicious.
Alright, so that's my problem. Two, 1. Alright, so, did somebody else do it? What'd you guys get for the mean?
3.33.
So 3.3. Did somebody get the standard deviation to work?
7.3896.
7.39, let's say. Again, whatever technique you use, don't screw it up like I do. Too late. Alright, so now we have to figure out E. How do we figure out E for this problem, folks? T crit, S sub D, square root of N. Make sure you take that square root. What's our T critical? What's our degrees of freedom for this problem, folks? 90% CI, degrees of freedom 11.
Oh, whoops.
Yep.
Sorry, that's 99. That'd be
Yep.
99.
Yes, uh-huh.
You said 1.796? Okay.
1.796 times the 7.39 divided by the square root of 12. .83.
Yep.
Awesome. So now that we've got our E and our D bar, what is our 90% confidence interval?
Low end is negative 0.5.
1.83 plus or minus, sorry, wrong way. 3.3 plus or minus 3.83. So the low end was negative 0.53. The upper end was 7.13. So technically, can this teacher say that he's guaranteeing his students that he does better at a 90% confidence interval? Technically, no, right? Because, yeah, there are some negatives in here, so statistically, he can't make that claim.
He's fired.
Yeah, true.
Probably a tenure.
Yeah, if he's got tenure, you can't fire him anyways. All right, not bad though. Again, almost the hardest part about this thing is making sure that you go back and remember how to calculate standard deviation, which will be a good exercise if it's been a while. Again, remember chapter 3. There's actually a statistical functionality in this, literally. If you just type it, yeah, where it says data and stat bar, you just enter in the data. You say how many of each number you have, and then when you're done, you say calculate statistics, and it will actually calculate standard deviation.
Under one variable.
One variable.
Or, where you find that again?
You see right underneath the arrows where it says data and stat bar, those two buttons are actually how you can do statistics on the calculator. It'll actually do standard deviation for you.
Oh, yeah.
Again,
AR, which is variance, I'm guessing.
yeah. You just as easy to use Excel, plug the numbers into each cell, and then highlight them all and say calculate standard deviation is probably easier, though, in my opinion.
I'd rather practice a little.
Not a bad
Have
idea.
Computer on the, well, we won't be able to.
Yeah, it's open book, so.
What if you log into the computer all this stuff?
Well, yeah, true. Hopefully you don't do
Entire problem is messed up.
When your calculator all messed up.
Well,
All right,
it's messed up in
so-
general.
So moving on, 9.4. We've compared means, we've now compared dependent means. Now let's move on to what we would normally go next, and let's compare proportions. Slash percentages. So compute confidence intervals for the difference of proportions. So p hat 1 minus p hat 2, and just like before, there is going to be an error value plus or minus the error. And the error calculation you are going to get for this one is going to look relatively familiar, but not quite exactly the same. It's the z crit times the square root of p hat 1 times 1 minus p hat 1 all over n1 plus p hat 2 times 1 minus p hat 2 all over n2. And again, that should look relatively familiar because that's again what we were doing back in chapter 8 and even back in chapter 6 and 7 when we were dealing with proportions and trying to find out standard deviations with them. Very similar type stuff. Note, folks, remember on the last test, the very last question, what had to happen? N1 times p hat 1 has to be greater than 5. N1 times 1 minus p hat 1 has to be greater than 5. All of those things have to be true for both populations.
So we have to do it for N2?
Yes.
Oh, you do.
Yep, we gotta do it for N2 as well. It has to be true for every single one of those. If any of those are less than 5, you can immediately throw your statistics away and say, we can't calculate anything, okay? No guarantees, I did it once, there's no guarantee I'll do it again.
Saves you time grading, so.
I'm
Here we
saying
go.
that's bullshit.
Some right, some you're like, gone.
No, I gave everybody 4 for that one.
Wait, what?
For that last question where you didn't do N1. So you were the only one, Tequila, who actually got 10 on that one. Everybody else got 4. Alright, so again, don't forget to check these. Anytime you're dealing with proportions, folks, this has to be true. Okay, it just has to be. No matter what you're doing, right? And this will be true for any time else that we come back to proportions and deal with it again later on. This sort of stuff will still have to be true.
Did you say that you were gonna do, is it a cumulative, so we'll go back to the first section, or no? I didn't know you were gonna go all the way back to me.
Some of the stuff you're going to be doing again anyways.
Well, because it's part of the equation.
Yeah.
But I was just wondering if you're gonna add everything.
Yeah, no, I'm not going to go back and ask you for like 25th percentiles or, you know, draw a graph and have you analyze the graph. Or... All right, so let's see. Let's just do one from the book right away. I don't want to come up with something screwy. Let's just do it. So I assume I asked 4, 8, 12, 16, and 20 again?
Yeah.
Pretty much.
Well, actually, you did 5, 9, 13, 17.
I did a whole bunch of odd ones.
Just to change it up.
All right, so let's see. Let's do. All right, let's do. Did I assign 22?
Mm-mm.
All right, let's do 22. All right, it's a good question because it's talking about state politicians, which since there was an election yesterday, I'm like, not a good thing, not necessarily a bad thing to go over.
I didn't even know that there was. I was just about to say that. Yeah,
I don't vote.
no
For
clue
good
until I went to class last night. He's like, "Did you vote?" And I was like, "Didn't know there was something to vote for today." I feel bad. Apparently, some type of person in the Senate and.
Yeah, well, I don't know which district you're in, but for Dane County, there was just a judge, the national judge, or the statewide Supreme Court for Wisconsin.
There you go.
Did you hear that we still have a treasurer?
Yes, I don't want to amend the Constitution to remove it, because if we need a treasurer at a later date, we would have to re-amend the Constitution to get it back. Right now, they've basically made the job a pointless job. And,
I mean, he still does like one thing.
yeah, he does like about one with like 2 or 3 other minor things that he does. But yeah, I mean, that's because the current governor has been constantly taking that position's jobs away from them.
State legislature's been doing it since
Oh, yeah.
95.
Yeah, exactly. So eventually that's gonna flip. And when the legislature and the governor flip, I would like to think they would start giving the person the job again. The salary is only like 66 grand too,
Yeah.
so it's like.
Only make more than those teachers we were talking about yesterday.
But this is a politician, everybody knows they're more important than teachers.
Yeah, come on, duh. I don't wear a suit and a tie and walk in Madison all the time. True. All right, so anyway, the state politician is interested in knowing how voters in rural areas and cities differ in their opinions about gun control. Hey, wow, what a very topical question.
Oh my God.
All right, so rural, or if I could spell it,
Revolve?
rural versus cities, whatever. All right, so he surveyed 75 people in the rural areas and found that 41 support gun control, right? So X is equal to 41.
That's not the X bar.
No, it's not the X bar. And he sampled 75 people from a city and found out that 53 people in cities were trying to claim that they were approving or supporting gun control. And we want to find 90% confidence interval, 90% CI for the proportional difference. All right. Now, remember these are Z-crits, so. All right, now, first off, what's P hat 1?
0.55.
How'd you figure that out?
I took X and divided it by N.
Good. 41 out of 75. And for simplicity's sake, let's round to 2 decimal places. What'd you say it was?
5.5.
And what's P hat 2? I mean, you can write it as 55%, but proportions are always decimals, so. So what's 53 out of 75?
7.1.
So 0.71. In theory, 71% of people in the cities were saying they supported gun control, whereas 55% of the people in the rural areas were saying that they support gun control in this particular survey. All right, so. What's going to be our E? Z-crit. What's Z-crit for a 90% confidence interval?
Is that nothing here?
Yeah, that's a nice little one, right?
Okay, yeah.
1.645.
Yep.
And then we have to find out what times the square root of 0.55 times 1 minus 0.55 all over 75 plus 0.71 times 1 minus 0.71. If I could write that number again. All over 75.
Oh my gosh, so I had totally forgot that the crit value was in here, and I've been flipping through the book.
Oh, we tried to get to the page where it's
There's like 3 different pages that have it.
Right.
And I was like, why is this not on here? And I forgot all about you saying that.
That's the Z critical value.
Oh, okay.
Yeah.
I don't think I'm gonna read
You can also use table A or B. It's on table B, right, technically. So if you turn to the front of the page, to the front of the book, it's that table at the very bottom with just the numbers. So 90% is the 0.10.
Times 0.45 divided by 75 plus 0.71 times 0.29 divided by 75.
I hope I don't screw that up.
Did you guys get 0.1279?
Now I did. I didn't finish the last part.
Are you doing that 4 decimal or are you gonna small it down?
I'll small it down.
Are you gonna, what decimal do you want us to go to? Is it just off of what we have above?
Yeah, it should be off of, yeah, since we have 2 decimals up here, you should probably do it to 2 decimals down here. If you would have done these percentages up above to 3 decimals, then you should have done your error value to 3 decimals. Generally, that's, your error and your difference value should be the same number of decimal points normally. So, 0.71 minus 0.55, what is that? 0.16? So our 90% confidence interval is 0.16 plus or minus 0.13. Subtracting. The true difference between the proportion of people that think there should be gun control between rural and city is somewhere between 3% and 29%.
Then they should have it or lose it?
They should have it.
Oh, that's really small. Is it?
3 to 29%. Again, the true value is anywhere inside of there, so it could be closer to the 29% or it could be closer to the 3. The thing that they would be using this for would be to say that cities generally want gun control more than rural places, right? And this validates that, right? Because it's at least 3% more up to 30% more. But it's at least more than 0, and that's what they're really trying to show.
And they only had 75 people out of the area.
Yeah, true. They could have sampled lots more if they wanted to. And if they would have sampled more, this range starts to get smaller and smaller because that
So the
This
more people you
75.
sample, the smaller it gets.
exactly because you're dividing by a bigger and bigger number, so these numbers become smaller and smaller and smaller.
And then with the 90%, it gets bigger, the closer you get to the bigger percent.
Yes, the bigger you make this number, the larger this number will get, therefore the wider your range will go. And again, it's purely a matter of where the numbers are, right?
Yeah.
These numbers are multiplied, these numbers are divided.
You said it.
Well, it makes sense, right? I mean, if you multiply by 2, it's going to make your number get bigger. If you divide by 2, it makes your number smaller. So that's the difference between sampling 1 person versus sampling 2. So if you divide by 3, it gets even smaller. If you divide by 4, it gets even smaller, etc. Hence, ask more people if you want a tighter approximation. Again, the key to that, though, is that when you're asking people, please try and make it random still. Right? If you only ask people that have a gun rack in their truck out front, when you go to sample, guess what? And again, that's another one of those things where when they say random, you want to believe that they're really being random, but you often have to look at their pocketbook to determine whether or not they're really being random, right? I mean, if someone's paying you $100,000 to do a survey on gun control, and it's the NRA, they probably want you to say that there shouldn't be any, right? I mean, and you know that that's what they want, and you really like getting paid $100,000 a year to do a survey, right? Yeah, exactly. I'd be going, yeah, we should not have any gun control, man. Come on, and there, slide another 100,000 right there. Thank you. Right? I mean,
At least then you can go buy more guns.
I'll just give them the ultimate statistic.
I'm just saying.
Take the money and tell them 60% of the time, we said retire.
All right, so not bad with the difference in proportions. Again, the key to this one, I wanted to make sure that you remembered how to calculate the proportions when you're given a sample, right? The whole X over N concept, all right? All right. All right, so then the last one, the funky one, all right?
Great.
Oh, you don't like it.
Yeah, when you say it's funky, means it's not gonna happen.
What? Come on. So if you think back to chapter 8, what was the last section we did in chapter 8? Yeah, when we were trying to figure a confidence interval for standard deviations or variances, right? So in 9.5, instead of finding a confidence interval for one sample deviation, sample standard deviation, we are going to want to compare those. Yeah, compare variances or standard deviations. Into populations. Now, why would we give a crap about comparing two populations' variances?
Because someone needs to know it.
Very true. Can you think of a reason why someone might want to know this or calculate it?
Really
Oh, the present.
Yeah, I mean, you could compare, say, Wisconsin citizens' desire for voting for a president versus, say, Minnesota's, and then try and talk about the variance of the population's desire for a specific vote. But think about it in a manufacturing perspective, right? I mean, if you're running, say, a car manufacturing plant, do you just have one line that produces cars? No, you maybe have one or two or three, right?
Or ones that specialize in certain parts.
But is there a good chance that you have two lines producing the same thing? Would you want to make sure that the variances of those two lines are basically the same, so that they're not producing different types of materials? You want to believe that their variances are basically the same, right? Because if they're not, then the lines are somehow off in their production, and that's going to be a bad thing, right? So you want to check that. You want to compare.
So when you say variances, sorry, I'm like getting kind of dumbstruck. What do you mean by that?
So the idea is that on average, the line is always going to produce a car that weighs 2,000 pounds exactly, right? And what they're doing, though, of course, is that's the average, right? But if the average is 2,000 because the first car they produce is 2,010 pounds, the next car is 1,990, then the next car is 2,100 pounds, and the next car is 1,900 pounds, so that there's always one that's down or up. And they're always different. Instead of being really close to 2,000, there's just always one that always matches the other one going the other direction. The variance when that happens is really high. But the average is still going to be a nice, even 2,000, right? But you want to know that, right? Because if you're producing a car that's supposed to weigh 2,000 pounds and it really weighs 2,100 pounds, that's really bad, right? Its gas efficiency is going to be way worse than the one that weighs a lot less. Or worse yet, it's not going to have the torque that it needs in order to actually drive the right way, right? So they're going to be looking at the variances in their values just to make sure. And this is the way they'll do it, right? Is using this technique, all right? All right, now, remember, variances / standard deviations are squared data. What this means is that we are not going to be able to get a nice plus and minus e, okay?
There's like no more stairs on this side.
Yeah, I don't want to know. We can't use And if you think about it, back in chapter 8, we couldn't use that for chapter 8 as well when we were just looking at one variance or standard deviation and trying to figure out its confidence interval. All right? So, well, it's even worse than chi-square.
Oh, God.
It's getting worse.
It doesn't fit on the fold out.
What?
You're going to have to use tables at the back of your text.
What's
So-
that?
If you guys pull out your textbooks
Oh,
and turn to page Appendix A and turn to Table F. Well, actually, it's not F. Got to go past F. It's Table H.
Okay.
which one?
Yeah, notice if you keep turning the pages for Table H, what?
am I looking at?
Uh-huh. What the hell are you looking at, folks? Notice how long Table H lasts. Yes.
Jesus.
Yes. Welcome to Table H. Like I said, this is screwy. Okay.
Oh, why was I?
Because we need to compare standard deviations or variances. And now what we're trying to do is to compare to squared values, and it just starts to get ugly. Okay? So,
That's almost 20 pages.
we need to use the F statistic.
No, it's double. He hides his statistics.
I'm pretty sure if you look in the basement, something like there's a Satan one that says something about, and then Satan put algebra in math or like alphabet.
Is this in algebra?
I'm just saying they co-op a little.
All right, so the nice part about it, okay, is that the actual formula for calculating the confidence interval is relatively simple, okay? Right? So we do the comparison using division instead of subtraction. So instead of doing the standard deviations minus each other, we actually put them over each other. All right? Now again, we're trying to determine how different these standard deviations are. If two standard deviations are the same, if you take something and divide it by itself, what do you get? 1. So the key to working with these confidence intervals of the comparison is how much do they differ from 1 as opposed to how far do they differ from the difference between the two values. Because now we're doing division comparison instead of subtraction comparison, which is just slightly different. Okay? So your confidence interval for standard deviations so you're just going to divide your two standard deviations. That's all you're going to do. And then you're going to multiply by 1 over the square root of the F statistic. And it's alpha over 2, where alpha is, again, 1 minus the confidence interval. And then the upper level of your confidence interval is, again, just the division of your standard deviations. And now instead of getting alpha over 2, you do the 1 minus alpha over 2. And the idea is that somewhere within this range will be the true quotient of the population standard deviations. And again, you're looking for numbers that are more or less than 1. If both of these numbers are less than 1, then you can say that S1 is less than S2. If both of these numbers are greater than 1, then you can say that S1 is greater than S2, because that's how 1 and less than 1 work, right? We know your division algebra to some degree. Alright? Note, if you're asked to calculate the confidence interval for variances, this is just looking for you to square everything instead of square root it. Everything is exactly the same, except now you deal with squared values, and you don't square root your F statistic. Don't like my fishies?
I don't like to know how to make them. You get what I'm saying, the fishies?
Yes, the alphas.
Yeah, I don't like making them because I can't do it without like starting a fish and like peeling it back around.
That's fine. Whatever it takes to finish it. So just note the difference between standard deviation and variance. It's the exact same difference that we have with them right now. Standard deviations are the square root of variance, so adjust. All right, now how do we read these whacked out tables? Okay, so first off, if you notice the pages, folks, as you start flipping through them, you will see the alpha value start going down as you flip across, right? So it kind of does 3 instances of each alpha value, and then it will go down to the next alpha value. So you see 0.995, and then it goes down to 0.990 all of a sudden. Keep going, it'll go down to 0.975, etc., etc.
Why is there so many for the same value?
Well, there should be 3 tables for every alpha value,
Why?
because you have to deal with all the degrees of freedom that might exist. And if you notice, what's different about it from the same number to the same number is that the number of degrees of freedom keeps shifting, right? So if you look at the first page, it always goes from 1 to 9, and then you look at the next page, it goes from 10 to 18, and then the last page, it'll go from 19 up to 120. Okay?
I just noticed the bottom is
Yes.
degrees of freedom. Unlimited.
And note, folks, what I tell students is that I am not, a lot of times in this class, we would spend a lot more time on this, talking about how to extrapolate values that are not on this table. So imagine, if you will, that one of your degrees of freedom was like 35. Is 35 on the top part of this table?
No.
No. And so this is where a normal mathematician would spend a few days talking about how do you extrapolate to 35 between 30 and 40. We are not going to do that in this class. If you get an n that is not exactly on the table, please round it to the closest one that is on the table.
I was going to be correct, you just happened to get there that way too.
That's probably.
That's a linear extrapolation. This is not a linear graph. This is a quadratic graph, and so you have to actually square root extrapolate from one value to the next. Because the graph from one point to the next is not linear. It's making a curve, and so you have to deal with that in your extrapolation, which is why it is fun. Ben, you would have a blast if we got to do it. I know you would, but I do not want to spend a week doing it, so I'm not going to. All right.
You had that too. You lost me at extrapolating.
Well, extrapolate, right? So the idea.
I've never even heard that
I'm
word
just gonna
before.
consult an oracle.
Yeah, you have. Right, so if I said the value at 10 was 2.5, and I said the value at 20 was, say, 3.0, what would you assume the value at 15 is if at 10 it was at 2.5 and at 20 it was at 3? Exactly. That's known as linear extrapolation, right? Linear extrapolation is saying, well, how far am I between my values? That's how far I am between here.
I've never heard you say extrapolate.
Well, it's because we haven't done it. But that's what it means, is extrapolating or finding a value between 2 known pieces of data to a value that's not known, but you should be able to figure it out.
Right, I got that.
Yeah,
Part once you got it.
The problem, though, is that
Linear.
yeah, it's a line, but what we're doing is more quadratic, and so you can't say that it's going to be half. That assumes it's linear, and this stuff isn't. And that's why we would
There's actually a way to extrapolate using square roots if you wanted to learn it.
Word of
To
the day,
extrapolate quadratically, that's a great phrase to write down. You should do it. See if anybody gets it. That's cool shit. I mean,
You know what someone's gonna think because I'm in the nursing kit? They'll be like, oh, did you do something today? No, not at all.
yeah, I extrapolated my phi. It really hurts.
Exactly. They're gonna think it's some medical term for like extracting something.
All right. So, anyways, folks, this is how it's going to be done. Now, note what it says in the table, right? It says numerator degrees of freedom along the top. Note what it says along the vertical, along the up and down sides. The denominator degrees of freedom. Okay? There is a numerator and a denominator for your populations. This is commonly called the numerator. This is commonly called the denominator. So when you figure out your degrees of freedom, the numerator is the S1 population's number of degrees of freedom, and your denominator is your S2 degrees of freedom, n minus 1, again, for both of them. All right? So, are we ready to try one? Alright, so degrees of freedom, numerator equals S1 equals N1 minus 1, N1 minus 1, and denominator equals N2 minus 1. Alright, so let's find a problem in the 9.5 questions that has two different ends. So which ones did I assign in 9.5? Same thing?
You only did 3. Then there's a reason.
I only did 3 of them.
8, 16, and 24.
8, 16, and 24. Oh, look, 24's got different ends. Yes! Okay. Alright, so let's try,
You can see my level of excitement.
let's do 25, because at least 25 has two different ends, right? 15 professors and 14 students. Alright, so 9.5. It's like, no, you're done. Quit. Number 25. Okay. A graduate student walking around a large college campus notices that students, not faculty, often own the more expensive cars. Go figure. He collects data from 15 professors and 14 students on the price of their cars and calculates their variances from each sample, etc., etc. Alright, so N1 equals 15, because there's 15 professors. And the sample variance of the professor's cars. Notice, since he gave you variance, that's S1 squared, right? Variance is always squared, standard deviation is not. 2, 5, 2, 4, 5, 6, if I can read. 2, 4, 5, 6.45. And N2 is 14, and its standard deviation, sorry, its variance is 3567.90. We want a 90% CI ratio, or the ratio of the population variances. Of population variances. And note, 24 is also doing population variances, so you can follow the same example to do your homework. Alright, so here we go. The cool part about it is that it's really just a matter of plugging these numbers in, right? So we want to put S1 squared, 245.45 over 3567.90, and then multiply by 1 over our F statistic. So now your guys' job is to figure out what F is. First thing though, since it's a 90% confidence interval, what's alpha? 0.1, good. And so what's alpha over 2, folks? And note that that's how our F statistics are working. F sub 0.05 and F sub 0.95, right? So your first number, so turn to 0.05, which is towards the end of the set of tables. 0.05, and note, what do we want our numerator degrees of freedom to be?
14.
And what are our denominator degrees of freedom? 13. So on the 0.05 table, look up numerator of 14, denominator of 13. What'd you guys see? Awesome. That's one side, the other side. 2456.45 all over 3567.90 times 1 over. Now you have to go to the 0.95 table and do the same thing.
So why do you do that?
Because that's 1 minus alpha over 2.
Oh.
So remember in the formula, the first one you have alpha over 2, the second one you
Yeah.
have 1 minus alpha over 2. What was that? 0.3988. 1413. I buy it. And now it's just a calculator problem, right?
You say so.
So how come you don't square the second one?
Square these ones.
Is that what you have to do? We're doing variance, right?
They're already squared.
Oh, they already are.
Because they gave it to us as variance. Since they gave it to us variance, it's already squared.
Okay, that's why I was wondering.
Yep. Divided by 2.5536. Again, I'm just rounding to 4 digits because that's the way all of my numbers are. If you rounded it to less, that would be perfectly fine. So the true ratio of the variance is somewhere between 0.2696 and 1.7264. See, did the back of the book agree with that answer? It's gonna be close. Helps if you're in the right chapter.
That's pretty wide for the ratio, isn't it?
Yeah. Huh.
What does it say?
It says 0.5793 and 3.7090.
Close enough. That's fair.
That seems a little screwy to me.
Did you do it?
Zero question.
At least that's what my book says. I don't necessarily know if I trust it. You guys got the same numbers when you punched that out, right?
Yeah.
Yeah.
As long as we're on the same track.
Well, that annoys me. It should be.
So Barbie needs to get it all right.
Did they do it the other direction? 3567.9 divided by 2456.45 divided by 2.5536. Oh yeah, they did the ratio the other way. So the book did the ratio the opposite direction.
Why? Which was the first sample?
It doesn't really matter which one.
Yeah, it doesn't, except it does change your numerator and your denominator though. Makes me nervous, because honestly, it makes me think they did it wrong.
That's scary.
Wait a second, did you change your F value?
No, So they used
So they
these
used-
numbers in reverse,
they
but
did it
used the
wrong.
same, yeah, I'm almost sure the book did it wrong.
Almost sure.
No, you can be sure they did it wrong.
Yeah,
If you change
because-
their F value,
Yeah, if you flip these, you should use the different value, you should use 1314 instead of 1413.
That's funny, cause even on their like table thing, it has it put the same way we did it.
Yeah, uh-huh.
Damn it, Warren.
Yeah, it just means that, again, don't trust answer keys, that's all I have to say, folks.
Oh,
You
no
should
way.
contact the book company and be like, you did this wrong.
I'll look at it more when I have time.
should be
All right, folks.
2.5073.
What?
Should be 2.5073.
It's relatively close to the
Close, but it's not.
It's not the same, and the number that I got when I changed those values around and then put it in, it was, I don't know. Well, whatever. Again, please do things the right way. This is the right way, based on the way we set it up. Just because it doesn't match the way the book goes is fine with me. So next time, folks, for next week, if you would, please, the Chapter 9 homework. And if you haven't finished the Chapter 8 homework, please get that to me sooner rather than later, if at all possible. Thank you.
You're
What
welcome.
time are you doing tomorrow?
I am here like 8 to 3-ish, 4-ish tomorrow. I have free time from noon to 3, so.
That's fine, I probably will be around.
I do not have the Chapter 9 online yet, but I'll put them on there sometime today.
You waiting in here?
And I will be in Monroe on Monday next week, folks, so I'll get you all your stuff. At least that's the plan, unless it snows like a foot on Monday, and then sorry, I'm not gonna go to Monroe on Monday.
It is supposed to snow on Monday.
What did you get for a number?
I got .568789.
Oh, okay, so never mind, they did do it right.
Oh, they actually switched
They
it.
did have the right F values.
Okay. That's good.
We just did our ratios the other way.
Okay, I like getting irrationally angry now and then.
Oh yeah, stop the recording.